Alright guys, so we're going to be continuing today. We're talking about some more examples of U substitution, just taking over the topic itself. So if we go to the next PowerPoint, we talk about what we make U. Usually what we make U is something that you see the derivative of inside the integral. That's what you make as U. So what happens is that if it's the argument of a function, so if you see like a function and it's like x plus 1 to the power of 3, then you probably want to make x plus 1 u or something like that. So that's the argument. I think the best way to do this is to illustrate some examples. So if I have the integral of e dx cos e dx dx, what we see is that the derivative of e dx is indeed inside the integral. So it would make sense that I'm going to let u equal e dx. That's fine and dandy. And when I differentiate both sides, what I get is du equals e dx dx. And that's awesome because if I were to solve for dx by itself, I'd get dx equals du over e dx. So if I rewrite this, I'd go e dx cos u, and dx is now du over ex, all that times e dx. So what happens to e dx is that it cancels. And I'm left with an integral that I do know. And we all know the integral of cos, right? The integral of cos is sine. Don't forget your plus c because we're doing indefinite integrals right now. So what happens is now we sub back in u. So your answer would be sine to e dx plus c. That'd be your answer. What if we had something that looked like this? If we had the integral of x squared e to the x to the 3 dx. What do we do then? Well, I'll make u equal to x to the 3. Because I see the derivative of x to the 3, or like kind of the power of it, the derivative inside the integral. So I know if I take the derivative of both sides, I get 3x squared dx. I see x squared here and I see x squared here. That's fun. So what we can do is that dx really equals du over 3x squared. Sweet. So I can rewrite this as x squared e to the u du over 3x squared. These x squareds cancel. What I have is now the integral of u du over 3 du. I can pull that constant out front. And we know the integral of this would just be e to the u. So this would be halfway through the final answer. But this sub back in what u equals. I would go, but u equals x3. So e to the x to the 3 over 3 plus c would indeed be your answer for this integral, based on U substitution. So that's fine and dandy. Let's try another example, one where you have to use some other tactics. So you have, let's say, the integral of x over x plus 6 x plus 1 to the 6 dx. Right. This time I don't see the derivative of anything inside the integral. It's not like last time. So if I made u equal to x minus 1, that means x equals u plus 1, doesn't it? Just from algebra. And that's fun because I can rewrite this now as the integral of u plus 1 over u to the 6 d how can you differentiate this again? Well, this one right here, to get d to the u equals dx, right? To get something like that. Oh, sorry. Made a mistake there. That's what it should equal. So we write this as u minus 1 over u to the 6. So if I were to integrate this, I would just have, as a final answer, u to the negative 4 over negative 4 plus u to the negative 5 over 5 plus c. We have a minus 5, so we get rid of the negative and have a positive. So we sequence would have just x plus 1 to the power minus 4 over negative 4 plus x plus 1 negative 5 to the 5 plus c. Sweet. So even more examples for you guys. We have the integral 1 over x ln x dx, right? If I let u equal ln x, then the derivative equals 1 over x dx. That's good. Because now what I have is, because if I solve for dx, it's x du equals dx. So I get 1 over x times u, x du. These x's cancel, so I really get the integral of u to the negative 1 du. And the integral of that is just ln absolute value of u plus c. So it's kind of a weird question because the answer ends up being ln of ln x plus c. Okay. Sweet. So that is it for u substitution examples. Excuse me. Now we talk about the fundamental theorem of calculus. Okay? So what is an integral? An integral is essentially just the area under a curve. So this shade region and this shade region is what you're finding when you're evaluating like a definite integral. You actually have numbers to play with. That's what you're finding, the area underneath the curve. So now we get to the term definite integral. Up to now, we've been doing indefinite integrals. We have plus c's at the end because there could be multiple answers. Now we're talking about definite integrals. So what that is, it's just an indefinite integral. With a fixed interval. That's all it is. See, the notation would just be, we use a for the lower bound and b for the upper bound, and the integral of f of x dx. That's all we do. So let's try something easy, right? Let's try explaining this fancy term, the fundamental theorem of calculus. And it's not something, it sounds scarier than it really is, right? Because all it is, fundamental theorem of calculus, FTOC. Me and my short forms never stop in this course. So, if f of x is a continuous function on a comma b, including the points, then we can go a to b equals that 1 So remember, big F is the antiderivative, also known as the integral, right? So that's also how you write it as well, when you're done integrating. So going back to our previous example, if we have minus 4 to 4 of x dx, right? We have, now that after we integrated, we have. Notice that we've integrated already. Okay. You don't have to do that, so there's no s anymore. What you do is you sub in certain values now, right? You go 4 squared over 2 plus c, which is f of b, sorry, minus 4 squared over 2 plus c, which is f of a. Notice that the c's would just cancel, so you just have 16 over 2 minus basically 16 over 2 as well, so you just get 0. The area under this would just be 0. And to go back, it's saying that the negative area would just cancel the positive area. Yes, we actually have negative area now. So that's fun. So what if we had like a sine curve, right? What if we had this in our books, such as f of x equals sine of x? What if we had that? And then it's 0 to power 2 included. Here's a sketch, right? So that's a curve, by the way. Power 2. What would happen? Well, I would just do the integral, 0 to power 2 sine of x dx. And if I integrate that, I would just get negative cos of x, the upper bound, the lower bound right there, and your evaluator, right? So I would just do something along the lines of negative cos pi over 2 minus cos, well, minus cos of 0. That would be plus, essentially. So I have 0 plus 1, which equals 1. So the area underneath from 0 to power 2 under that curve would indeed be 1. That's how you solve that problem. Okay. I guess we could do maybe a harder one with like nothing with like polynomials, because that's pretty much light work. I have like positive 1 to the e of 1 over x dx, right? Then if I integrate it, right, I have ln of the absolute value of x, and my upper bound is e of 1, so I do ln absolute value of e minus ln of 1, right, which is 1 minus 0, which is 1. So the area from 1 to e of that curve as well is also equal to 1. So that basically sums up that note for today. So I'll make sure we're covering everything here. So next, we're going to be starting to cover kind of like vectors and getting to that part of the course to wrap it up.